we want to get into vector spaces and vectors in Rn. So we'll just have a brief lecture for today, and then we will continue this lecture on Monday. So we'll talk more about the geometry of vectors and vector operations. Right now, we kind of want to introduce the basics. So when we write r to the n, call this a blackboard bold. So we can't write bold numbers when we're just drawing, so we put this extra line in it. It is an n-dimensional space over the real numbers. So it's going to be tuples of length n, where each coordinate is a real number. So I'm not sure if you guys have seen this notation. This is set notation. You've probably seen it somewhere, maybe in Calc 2 or Calc 3, especially if you took calculus in the math department. I think we kind of introduced this to you at a baby level. But how do we read? This is really like mathematical linguistics here that we're writing out. It's like mathematical calligraphy in some sense. How do we read this as a mathematical statement in English? So the word, or the symbol equals, you can write as is or equals. So r to the n is, anytime you see this first squiggle bracket, means a set, or the set. Then we describe the set. So in this case, we have Rn is the set of n tuples. This vertical line means such that. You'll see this phrase such that quite a bit in math. It's kind of a transitional phrase. After we introduce a topic or introduce a definition, we want to describe this object in a better way. So it's an object such that certain properties hold. So such that we often abbreviate just S period, T period. And then here, these are properties of the objects. And actually, let's be precise, properties of the elements of the set. So here, description of the set, description of the elements in the set. So whenever we have Rn, we have 0, which is just the n tuple of all zeros in Rn, is called our origin. And again, this symbol here means element of. So this tuple is an element of our set, Rn, meaning that this tuple satisfies the definition of how we defined our set. And of course, it's the origin. Every coordinate is just 0. So of course, examples, we've all seen R. R2 is our Cartesian plane, and R3 we've typically described as the set of x, y, and z. But now we want to jump into potentially higher dimensions, R4, R5. And as I've mentioned in previous lectures, that sometimes X, Y, Z, W, as the dimensions get higher, we run out of letters. So when we have an arbitrary number of dimensions, we often just specify them all with X's, sometimes Y's, sometimes Z's, but most commonly X's with subscripts for the index. So for any point, P, which will have certain coordinates, we call the vector from the origin to P the position vector. So this is the line segment or the ray starting from the origin pointing to a point P. So for example, 2 dimensions are easiest to draw. Here's our origin, 0, 0. We might have some point P here. And let's just give it coordinates, -3, -2. Then this vector here, we would call the vector OP. And so we draw it exactly like that. We draw it as an arrow from the origin. So vectors drawn. As arrows from the origin. So typically now when we talk about Rn, we don't really want to think of points in Rn. We can, but since this is linear algebra, we actually want to think of elements as Rn as vectors. So not just a point sitting there in space, but namely the arrow that points from the origin to that given point. And so we typically draw them, instead of writing like OP with an arrow over it, we simply just use one letter, X, which we typically write as a column vector, X1, X2, down to Xn, as an element of Rn. So again, you can think of this as the tuple which would give us the point, and then of course the arrow pointing from 0 to the tuple. Here, I'll just say gives X vector. So some examples and things we've seen in R3. We have directional vectors. Our I. Sometimes it's drawn with a hat. Our book draws it with the arrow. That is the vector pointing in the x direction, so 1, 0, 0. So if you consider our coordinates x, y, and z, it's just pointing with a length of 1 in the x direction. The j vector points in the y direction, and then the k vector points in the z direction. More generally, we like to use this notation of E. So we commonly use these E's to represent our unit vectors within a given direction. And what it's going to have is just zeros everywhere. I guess we should put a 0 here. And then it's going to have a 1 in the ith position. And so this guy is an element of Rn. These are what are going to be known as our basis vectors, or our standard basis, which we'll develop more in the coming weeks. So generally, a vector is an object that has a size and a direction. So hopefully you guys saw this in Calc 2 or Calc 3. So for example, our P vector it has our direction. So this is why we want to consider them as arrows. Starts at the origin and points in a specific direction. Hopefully you've seen this in Calc 3 with directional vectors and tangent vectors. In Calc 1 and Calc 2, your directional vectors were only in 2 dimensions, and you often have to find the slope of a tangent line, which the slope in some sense gives you a baby version of a directional vector. In Calc 3, you generalize that as soon as you start to parameterize lines and curves as the tangent line to a given curve usually starts at a given point and then has a direction that it points. The size is given by the magnitude where for an n-dimensional vector, given by x1 to xn, the magnitude or the length of x is denoted with these double bars, kind of like an absolute value, except with double bars. So of course, absolute value in one dimension gives you the length or the size of the distance from the origin. And this is no different in multiple dimensions. It's just the distance of what you might consider the point or the tip of the arrow, sort of the length of the arrow, the distance from the tip to the origin. And it's simply computed by our typical Euclidean length, where we add up the sum of squares of all of the components and then take the square root. Okay, so let's try to formally develop this notion of a vector space now. And first, we want to know what types of operations we can do on vectors. So we have scalar multiplication and addition. So for any vector, let's say for vectors x, and y, in Rn, and scalar t in R, we note that t times x gives us a new vector where we can simply multiply each of the coordinates by t, and that gives us a new vector in Rn. And we can also add two vectors, x plus y, by adding coordinate y's for each coordinate. And this will, again, of course, give us a new vector in Rn. So, what is a vector space? So, definition. A vector space we will say in Rn is a set of vectors and let's give our vector space a name. So a vector space V in Rn is a set of vectors And let's call the vectors V. So it's a collection of vectors such that for any B, W, and V, and scalars in R, so any vectors in V and any scalars in R, we have the following properties. So one, we will say there exists nah, I don't think I want to write that. We can derive some of these properties that are going to be important to talk about. So one, V plus W is always an element of V. And T times V is also an element of V. In other words, whatever set of vectors we want to define, I should always be able to add any two vectors in my vector space and still get a vector within that vector space. And we should be able to scalar multiply any of the vectors. So from these two properties, so some things we want to note is one, so for any, if I draw this upside down A, it means for any. So for any vector in V, by definition, 0 times V also has to be in V. In other words, the origin or the 0 vector is always within the vector space. So 2, again, for any vector V in V, we also have that minus V is in V. So our minus V we want to interpret as the vector that points in the opposite direction. We'll talk a little bit more on Monday about these properties and how we can sort of deduce some geometry out of them, as well as the geometry of scalar multiplication and addition. So not only is a vector space pass through the origin, but it's going to be symmetric in some sense. For every vector that points in one direction, we're also going to have a vector that points in the opposite. So namely, additive inverses exist. And we should note that V plus minus V gives us the 0 vector. So let's maybe do one example. I want to get you guys started on the exam here. Let's just do an example. So let's define V as a subset of R2, where V is equal to, let's say, all scalar multiples of the vector 1, 1. What does this mean? So we're going to get in, this will be a little bit into the geometry of scalar multiplication. But if we have the vector 1, 1, essentially what this means, if I can take all scalar multiples, is we are going to extend it both in both directions, right? So we can go in the negative direction. Vector spaces have to be symmetric about the origin. And so it's a collection of all vectors that have some scalar multiple of this given vector. And so we want to show and go through some of these basic properties and show that a line through the origin is going to define a vector space. And then likewise, in 3 dimensions, we will see that planes through the origin define vector spaces. Any questions? Okay, so we'll continue this on Monday.